Turning things on helps. Okay. Good. Welcome back, everyone, for the second day of Enzyme Conference 2024. The second day is still organized by the same people as the first day, and will be the third day. We have a denser program today. We have 2 talk sessions with 4 talks each. We have a lunch break in between as a reminder, and to be fair to the people who are watching the live stream, there is no lunch provided, but there are plenty of options around. We can discuss them. There is, however, coffee at the back of the room if you want it, and some snacks. And after the afternoon coffee break, we'll have a round table / panel on building the AD benchmark suite. I don't think I have anything else to say.
I think that's it.
So without that, let's start with the first talk by Michelle on differentiable and portable Krylov solvers.
Hello and good morning. This talk I submitted a while ago, though I was late even for the submission. But back then we were still full steam on exploring Krylov solvers for putting certain algorithms to the GPU. And something has changed drastically in the meantime that I will go also into in the talk. So Alexis Montoison was joining us from Quebec, who works on the Julia package Krylov.jl. So Krylov package in Julia, written in a portable way so that you can run it if you have a vendor blast, you can run it anywhere you want. And then I also found out last week that Jan was also doing some work and presenting it at EuroAD on Krylov solvers that I have integrated here. And Paul, okay. And I did not know about that. I was also not at EuroAD, so that's mine. So I will do a bit of a broader talk. I will talk about Krylov solvers and how we deal with them using the enzyme rules in Enzyme. But I will also talk about direct solvers and differentiation more in general. The background of this work is that we had to transition nonlinear optimization code to GPUs. Traditionally, these solvers rely on direct solvers because they have sparse, unstructured, ill-conditioned matrices. There's also nothing you can do about that, so there are no known good preconditioners, although we tried again this time, because the physics and how power grids are laid out, you cannot just refine the mesh and the scalings are just the way that they are. And the goal was, this was funded by the Exascape project, so we had to be portable to Intel and AMD. We could not just call the CUDA solvers and be done. Now, what is also after everything, it came down to the linear solver again, and I think that is a pattern that one sees oftentimes, that is, once you have ported your code to the GPU, have done all the fun stuff, and you have a linear solver, you will most likely be reliant on the linear solver to get performance out. And it's probably not the hottest topic right now. Probably there's someone working using machine learning to solve linear systems. But this is where we were stuck. So, and we were no linear solver experts. Our group consists of optimizers, power grid engineers, and CS people, so we still had to look into it. So I want to go differentiation of numerical function implementations, like some notions that we used to use in AD, like continuous versus discrete, and either differentiating through a function or applying what is called continuous adjoint. So you derive the adjoint on paper and then implement that. And of course, there's also the classical pitfalls of AD that I'm not going to go into. Like if you have if a Krylov solver, for instance, if you give it the starting point is the solution, it will return you the wrong derivative, and I personally had to suffer through that while I was working as a research assistant. So sometimes a solver which had somewhere in there a Krylov solver would just return wrong values because it was getting a point that was near enough to the solution. So differentiation of functions. So the basic functions, you have to. The computer is a discrete machine, so at some point you will move to a discretized space, which is the floating point numbers. And so you have always two choices when you have a mathematical model. You can either differentiate and then discretize, so differentiate at a high level, do it on paper, or add an enzyme rule for it, or do discretize and then just differentiate using the AD tool through it. But even if you do that route and go fully AD tool, at some point you will hit the discretized space when you do arithmetic and special functions probably. Those are the first two that you will be hitting. Like cosine and sine are not the analytical cosine and sine, but they are implemented using some series expansions. And we also, in the power grid formulations, there's often, for instance, formulations used polar formulation, which use polar coordinates. And these usually work best. And then you realize that on the GPU, for instance, the precision of the cosine and sine is less than on the CPU that you are used to. So there are some issues there. And then when you differentiate, you incur that error again, etc. So where to apply differentiation, that's essentially, so in Julia, the enzyme has now a package called enzyme rules, or it's an extension, or is it? I think it's, yeah, it's in enzyme proper. So you can define your differentiation rules as a user. And I think also, in the beginning, the AD tools always had, the rules were built in. Like every AD tool came with its own rules, which also then led that certain AD tools would behave differently. I think it's a good idea to have one set of differentiation rules and then apply them to all AD tools so that you have consistency in terms of how you apply it and expect actually the same result. There's also a nice package in Julia, chainrules.jl, which I liked from the very beginning because it really has as an idea to have common chain rules, common differentiation rules, actually, it applies the chain rule there. And then the AD tool actually applies the chain. Yeah, and then to use that as the base for all the AD tools that popped up. Now, Enzyme doesn't use that because chain rules uses, because of technical issue, because chain rules uses a closure in its API when creating a rule, and Enzyme doesn't like that, so I think that's basically what it comes down to, the gist of it, right? So model consistency, that's then often used when you talk to AD people, I think, if the discretized and the continuous model match. So if you go either way, you come to the same than what you would expect from your mathematical model that you, so your physical model that you have. As long as you take a path that gives you the same result, it is consistent. Now, it's not necessarily so that you always want to have the consistent adjoints. Like in optimization, for instance, you sometimes want to have the derivatives of the discretized model because that gives you better convergence. So, or has been observed to give at times better convergence. And the special functions also I want to mention work that I did on with stats people, with Chris and Stein. There was some Bessel function that was not yet in chain rules, and we figured out a way how to make that also generalized. And it's by no means so that all the special functions are covered when you are doing AD. You will run into issues And they are always implemented by series expansions, or nearly always, I would say. And you need someone who knows special functions and how to do series expansions to look at it and derive you a appropriate adjoint or derivative. So one other notion, so there will be two notions. One's this continuous discrete, and then we go to iterative algorithms. That's also one of the common problems that one runs into. You use an iterative algorithm, run it until you have a certain tolerance or criteria, and then you differentiate that and expect that that tolerance is good enough for your derivative, but that's not necessarily the case. So there's a common class of problems, fixed-pointed iterations. So if you are, they have a region where the value goes towards, gets attracted towards the fixed point. Trade-off methods are not strictly speaking fixed-point iterations because they give you they just happen to look like you are diminishing the residual because you're using trade-off spaces, but essentially you get the exact solution after n steps. So plus minus, of course, again, floating point errors. So for fixed point iterations, though, there are enough papers on that, on how to apply it, one-shot method, piggyback, all revolve around that notion, how you get, if you have a fixed point algorithm, how you make it converge for the adjoint. So you first converge the primal, and then you start from the solution and converge the adjoint, for instance, and so on. Machine learning is technically fixed point iterations, and special function implementations are also often fixed point iterations. So now differentiation of the linear solvers then. So usually linear solver is just another function. You get a and b in, x out. So the quantity of interest are the derivative of x with respect to a and b. And you then want to compute, when you do reverse, there are two adjoints that you might be interested in. Usually, most of the people already, they see A as constant. So they are only interested in the adjoint of B. They are not interested in the adjoint of A. The adjoint of A is a outer product of two vectors. So what you get out is a dense matrix. And this has been, I mean, if you look that up, this is probably trivial math for someone who does math. But a proper write-up is hard to find. I mean, this is still the best write-up, which are my colleagues from back then, but still, even if you look for it, they have really the best write-up, I think, in deriving the expressions and also comparing continuous versus discrete. So sparsity is, for instance, not conserved. You have a sparse A going in, and the adjoint is then dense. So for instance, you then want to do, for dense, it's OK if you have, of course, if you only use BLAST, that's fine. For sparse matrices, it will become dense, so you might want to implement some lazy solution evaluation of the entries. We had then, while writing the rule, so for enzyme rules currently only covers dense, if the linear solver is covered. But for sparse matrices, then the question arises like, what will you do because A is dense? Now, I had discussions with Billy there too. Although this looks like a problem here, your program should never access those entries that are non-zero, that are outside of the sparsity pattern. So, but still, I mean, yeah, users do stuff, so yeah, it could still happen, and then maybe the user wouldn't know what is actually happening. Then I thought, okay, nice, now I have understood all this, I can just go ahead, and Billy said, oh, why the Turing.jl people, they need a Cholesky, why don't you go and add a rule for that? And I went ahead and said, yeah, this will be fast. And I added essentially just treating Cholesky as if it were this. So I was abstracting away the factors. And in chain rules, there is an implementation of this. I think I could not find out who actually wrote it, or could I? And there's a paper from 2016, so very recent, where some machine learning guy was trying to differentiate through a Cholesky and was actually deriving how you compute the adjoints of the factors. So usually it's called in that way that you compute the Cholesky over a matrix, you get a nice Cholesky object. So the user usually doesn't access L, right? Though, of course it may, but most of the time it just uses Cholesky to solve for multiple right-hand sides and save the factorization. The adjoint of A, again, might not be symmetric. So there you have the, is pretty much for sure not symmetric. So you have, again, in Julia, for instance, and also in C++, you probably implemented it in such a way that you have, that your symmetric matrix is a type. So the type of the adjoint is not the same as what goes in. And yeah, the user should have, probably the user needs a choice there. Like, does the user want to have the factors? You can find that out through the activity, of course, but yeah, all these. And so we started out, again, coming to the beginning, direct solvers on GPUs. And the status as of 2018 was that there was no fast, robust, portable, sparse direct linear solver for our problems on a single GPU, single problem, not distributed anything. Just wanted to be faster than a CPU and not be just as fast as the CPU, because you have this expensive GPU, so it should also be really, you want to have something really faster, right? You want to use the hardware and be faster. So here are a bit of worthwhile mentions from back then. There's the review paper from our team on the various linear solvers for GPUs. SuperLU, which is for large distributed PDEs. Ginkgo is, I think, is a portable sparse linear solver written in C++. And I think they're also working on a Julia interface, so I'm really looking forward to this one. And then Cholmod, of course, was tried through CUDA and AMFPAC. Sprawl was a promising candidate, but I think development there has, if I'm not mistaken, stalled a bit. So our choice was clear. I mean, we wouldn't be developing our own linear solver. That would be a bit, so we have to try Krylov methods again, because this was tried on this problem a lot of times before, but we were hoping that maybe we can find a preconditioner that was not reasonable on a CPU, that would be reasonable now on the GPU, and maybe then it works. So first complaint, of course, is the vendor provided linear solvers, well, especially NVIDIA, are black boxes, which we'll see soon in numbers what the issue is with that. You cannot look into them. You don't know what they are doing. You don't know what runs on the CPU. Sometimes people are, I mean, we were benchmarking and then finding out that actually most of the solver was essentially just copying everything to the CPU, solving there, copying back to the GPU, then what are you benchmarking? Yeah, so Krylov methods only need the blast calls. There we should be safe. I hope that the blast calls is a safe API. The reason why direct solvers are so bad on the GPU is because of the pivoting, for one. So that's a global operation. So you cannot, if your system needs pivoting, that makes it slow. If you can use, that's why also Cholesky is probably your best bet on a GPU. If you don't use pivoting on a Cholesky, that's probably your best bet. And minimal fill-in, so you do reorderings of the matrix that incur minimal fill-in, so that and that also reduces the global operation. So those are the 2 points we would have to be working on, finding either not use pivoting, and then find some ordering that is specifically for the GPU, although there is Metis and AMD, which are very old codes and probably are very good at what they are doing. So I don't think we would find something better. So what is Krylov.jl? Yeah, Alexis is the lead developer there. It's a collection of Krylov methods written in pure Julia. He, by the way, finished his PhD now. If you want someone who knows linear solvers and really knows how they are working, and a good coder, can send him a message. So it runs transparently on the GPU. It has no vendor-specific calls. It just uses the BLAST calls. And then we started, so he spent some time last summer at Argonne, and we spent some time writing a package called Krylov Preconditioners, where we did a common API to all vendor classical preconditioners, like ILU and incomplete Cholesky. In addition, we wrote a preconditioner in pure Julia, block Jacobi, that came from the time when we tried to find a preconditioner that works on the GPU. And the block Jacobi is in particular very nice because we did a lot of small blocks and then used a batched dense inverse in the blocks. So that is a regime, for instance, that you would never run on a CPU. So we had like really 1,000 of these blocks, and they would just invert, boom, on the GPU, and on the CPU you would wait forever. So that's a regime that you would never have before even run on a CPU. Then we also then started, that was actually what I wanted then here to mostly focus on diffkrylov.jl, which is differentiation rules for then krylov.jl. And it currently supports forward diff and enzyme, so enzyme rules, CG by CG step GMRES. And when I got there, let's first go, yeah, this is Jan's work. So he compared differentiating black box through iterative solver, through Krylov solver, and against applying the rule. And you see clearly that going black box through it does not guarantee, has less chance of success. That does not mean that you should never do it. If you are in that regime where it works, it might be fine for you. Actually, we had the discussion, right, with Klaus. So he was going black box through it and seems to be doing fine for his particular problem. So why not do it? It's just that your chances are lower. Probably at first you would want to go through it with a rule. And then, of course, YCG-STAB also seems to have a higher failure rate. And this is also because of the algorithm. Although theoretically, we also observed that, like if you use YCG-STAB in the forward run and then in the reverse run, it often fails because of it cannot find a direction, orthogonal direction. Or it is orthogonal, whatever. And it fails. And YCG-STAB is not guaranteed to converge, right, as opposed to GMRES, or minus numeric values. And restart.
The restart of GMRES has no guarantees.
Yeah. But assuming infinite precision, GMRES would converge, I think.
Without restarts.
Without restarts. Yeah. And YCG-STAB does not. And what often happens is that in the forward run, it works, for the reverse, it fails. And I then try to also look into the math behind it, and it shouldn't actually happen because the matrix, the transpose matrix has the same eigenvalues, so it should have the same distributions. But it can happen, right? And apparently it's because of the numeric.
There's no reason why it shouldn't happen. Like there's absolutely no guarantee.
Yeah.
Definitely happens.
Yeah. And I was surprised by it because I was thinking that if in the forward run it works with those, but it doesn't. So then that you have to also incorporate in the rule. Then if you use the YCG-STAB, you probably want to give the user a out-of-the-box experience where it works. So you want to switch in the reverse one to run to a GMRES. So and this is Krylov.jl. New feature also, which is interesting and might be relevant, is block GMRES. So this is based on the PhD thesis of Alexis, and he does a block GMRES where he uses, I think, the same Krylov space for all right-hand sides, So you can solve for multiple right-hand sides in the same Krylov space. Of course, it has some issues. If you pick your right-hand sides in the wrong way, it will break down, but it gives you good computational intensity because you can use the block blast calls on the GPU. The same cannot be implemented using BCG step at all, of course, because there you will nearly certainly fail every time. Yeah, preconditioners are not treated yet. I don't know. Yeah, I have some thoughts about how they might be treated, but nothing has been done there yet. And no sparsity treatment for so this lazy evaluation we haven't implemented yet. Forward mode uses automatically switches, so when you have the forward mode GMRS and you then switch to forward vector mode, you will automatically use the block GMRS, for instance. Then you can, this new block GMRS algorithm. So, and then what happened, so that was the status when I submitted the talk, and then happened that we got aware of QDSS, direct solver implementation by NVIDIA, released in 2023. And it's just super fast, and it's black box. We see that it is doing something on the GPU, something on the CPU. We see copying of data. It's currently in preview. They even give us early access. And the reason is that we then ran it. And you see here the residual Krylov solver, QDSS. And you see that QDSS has this weird outlier. So this is log scale, right? So the residual for a direct solver is much higher than for Krylov, which is weird. And we saw that happens sometimes, and it shouldn't. Probably they think it's a bug, and it could also be I mean, we expect it also to be a bug that they resolve over time. But the speeds are just exceptional. On all sides, so this goes from small matrix to large matrix. As long as your matrix fits on the GPU and has not too much fill-in, you will use QDSS. That's my opinion, at least. So there's no need to use Krylov as long as it fits on the GPU. It's a multi-frontal solver, so it is probably related to Cholmod, MUMS, and whatnot. There's also some development that they want to, Alexis wants to help develop a multi-frontal solver for that is open source. So this is a game changer for us, totally game changer. We can solve new problems much faster. Yeah, no, this is the conclusion. Yeah, thank you very much.
Questions? Two comments. So, I mean, we don't know because it's black box, but it could be that just because of round-off, a direct solver may be less precise than an iterative solver. I mean, that could actually happen because the iterative solver can sometimes iteratively refine to a point that...
We do that also afterwards, to be clear. I mean, we do, after we use the direct solver, we do iterative refinement. But it's just still weird. It's so extreme that it is still weird.
Yeah, maybe it's a bug, but like, there's still a chance that it's just numerics. And the other comment is if you actually want to work on the preconditioners, we have that on our list as well, so get in touch.
Okay.
It would be nice.
Where can I find you?
Other questions? Comments? Let's thank Michelle again. Good. Our next talk is by Joe on the many ways to take gradients.
Thanks everyone, thanks for the invitation to be here. So I'm at the MRC Laboratory of Molecular Biology in Cambridge, UK. And I've been there for about 2 years, but I started my group in October, and I'm looking to hire postdocs, so if you're interested in what's in this talk, do get in touch. So today I'm going to talk to you about the various different ways to take gradients through a simulation of molecules. Each of these methods has strengths and weaknesses, and I'm going to kind of introduce a new method for doing this based on previous work called reversible simulation, which overcomes some of the main drawbacks of reverse mode AD, and show how this is fast, it's accurate, and it can be used to train both molecular mechanics and machine learning force fields. Okay, so what is molecular dynamics? Basically, it's simulation of a physical system, for instance, a protein in water, by integrating Newton's laws of motion. So you start with some starting positions and starting velocities, and you define the force field, as it's called, which determines how things interact. You press play, and it runs almost like a video, and then you analyze it and hopefully learn something. These methods have given insights into biology and materials as well, and generally they work best when used kind of in combination with experimental data. You don't just want to be running some video game, you want to be running something which is based on and matches real-world data. And as we look to the future, we have more and more compute resources, we have all these amazing machine learning approaches, and in particular, my research case, we have really good protein structure prediction now, so these methods are going to become more and more important. So how do you actually do this? Well, if you imagine you have some coordinates, x at some step I, you have the masses of particles, you have some force function which determines what's attracted to what and the like, which is defined by some parameters sigma. Then the velocity is the first derivative of the positions with respect to time, and the accelerations is the second derivative. And so this is a second order ODE, and you can use Newton's second law of motion to calculate the accelerations. And so one example of an integrator to run constant energy simulations, which is basically just kind of vanilla simulation without anything on top, is the leapfrog Verlet integrator. So the forward step is there. Shouldn't be too surprising what's going on there. However, something that's going to become important later is that this is reversible, so you can run it backwards to numerical accuracy. However, when we're simulating, for instance, a biological system, we don't want to run at constant energy, because we're simulating a kind of, imagine a cube or something of a cell, which is in contact with a kind of infinite water bath and can exchange energy. And in fact, it has constant temperature and also constant pressure, but I'm neglecting constant pressure for this talk. So this is called the canonical ensemble. So we can use something called Langevin dynamics, which is defined at the bottom here by this equation, and it basically adds a friction term and a kind of Gaussian noise term, which represents this exchange of heat with the heat bath. And one example of a way to integrate this is the Langevin middle integrator, which is equivalent to the one to leapfrog Verlet, which I just showed, when gamma is 0. And this can also be reversed, although you do need to record the noise terms if you do that. Okay, so my kind of whole research direction is improving these force fields that define how everything interacts. And there's kind of two broad classes of force field for biology, which is my use case. The first is molecular mechanics, so you basically treat every atom as a point charge, and you only consider pairwise interactions. Very parallelizable, works very, 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 very fast on GPU, and traditionally that's been trained on both quantum mechanical and kind of condensed phase experimental data. However, we also have machine learning interatomic potentials, which have really been a huge topic of research in the last few years. The appeal here is obvious. They're universal function approximators. They're pretty slow compared to molecular mechanics, but the reason we use them is because they're way, way faster than density functional theory, and they can often get comparable accuracy. However, they're usually trained on quantum mechanical data because there's no obvious way to train them on kind of experimental observables. So what do we want? Well, we want a method that can train both of these to match kind of arbitrary given experimental data. It should be accurate. You should be able to apply it to lots of different types of data, and crucially, it should be scalable as well to any number of parameters. And so, because this is an AD conference, the way we do that is by taking gradients, ideally. So this is kind of my classification of all the different ways you can take gradients through a simulation. We'll kind of power through them, and then I'll introduce a new one. So, and I've also included here kind of what I would call no gradient methods, so manual adjustment, which is just guess and check. So the first of these classes I would call kind of numerical methods classes. So you basically don't get you don't use automatic differentiation or kind of get gradients at all. So traditionally, if you were training molecular mechanics force field, you would do at least part of the training completely manually. So you would just set some grad student on it for 5 years to guess and check parameters. For instance, this study on the right, this is a very well-known force field in our community, and really this whole paper is just them changing, a few key parameters. I think it's, 3 or 4 parameters that really affect things, with lots of long simulations and sampling to improve the force field. And so the advantage here is actually that, and it is a big advantage, is that you can just use existing software, which has been ridiculously optimized over many decades, and which is not compatible with AD. But the kind of obvious disadvantage is that it scales very poorly with parameter number. And typically, you can't train whole force fields from scratch, and certainly if you have machine learning potential with thousands, even millions of parameters, you're going to struggle. There are sampling approaches, like Bayesian sampling, kind of genetic algorithms, etc., that can make this more feasible. But even if you use those, it's unclear whether you can actually reach the ideal minimum. So a very popular approach from about 10 years ago, it's called force balance, which is based on kind of principles of statistical mechanics. So it's just, if you imagine you want to look at the value of some observable, some loss, over all possible states, the way you would do that is by multiplying the value of the loss L at each state by the probability of being in that state. And we know from Boltzmann's equation that the probability of being in that state is proportional to the exponential of the negative energy, that should say, divided by the partition function. And so you can basically differentiate this kind of whole expression, and what you obtain is this thing in the bottom right. And originally, when this method came out 10 years ago, these gradients were found using finite differencing. But now we can use automatic differentiation for this, which is both more accurate and faster. There's also an approach from a few years ago which could be thought of perhaps as a kind of extension to the differentiable version of this, which is called differentiable trajectory reweighting. And the idea is you use thermodynamic perturbation theory to kind of reuse the states after each gradient update if possible, so you can avoid recomputing the entire trajectory. In practice, you can only really do that as you reach the kind of the minimum of parameters when the loss doesn't change that much, but it can be a more efficient way to do things. And this is quite a nice paper where they introduce this and use it to train machine learning force fields on observable properties. However, like force balance, this suffers from one major drawback, which is that you cannot use it with observables that take in multiple states. Okay, each observable has to be just taking the coordinates or velocities at one state, and this is a problem if you want to train biological force fields on, for instance, NMR dynamics data, which we do. So going on to the trajectory-based methods, we have the adjoint method. So this was actually mentioned in the last talk. So basically, you differentiate the differential equation before you discretize it. Okay. So you can consider this a joint term A, which is basically how the loss depends on the state at each time point, and you can then set up these two differential equations and solve the whole lot. So solve the original, the adjoint equation, and the loss with respect to parameters equation, all in one single call to an ODE solver, which is quite a kind of appealing way to do things. This method's been around for a while, but it kind of broke onto the scene in a big way a few years ago at NeurIPS, and it's been applied to the molecular simulation case from Rafael Gomez-Bombarelli's group here at MIT. However, in some cases, it can actually be unclear how to best solve the adjoint equation, because although it's the kind of exact solution, it is fundamentally a different equation which you have to discretize. And that can run into problems, and there's a few papers which have shown that. And in our case, we're running a second order ODE, so that is a concern. So the method I've worked on for the last few years is what might appeal most to people here from an AD background is just to use AD on the solver directly. And it gets you accurate gradients with respect to kind of the forward pass, the primal integration. You do need to consider gradient explosion and vanishing, which is kind of analogous to the related problems in larger recurrent neural networks. So for instance, in some work I did recently, you basically run the simulation and then you extract the kind of interatomic distances, you compare them to the desired distances, and then you just click backward or whatever in Zygote or Enzyme, and that gets you the gradients you need. So the main drawback is really the memory cost of keeping all the intermediate computations in memory. You can use checkpointing, which this work makes very, very heavy use of checkpointing, and that's great. But for machine learning potentials, even checkpointing presents a problem, because if you have some graph neural network, you might only be able to keep 10 evaluations of that in memory. So you would have to checkpoint every 10 steps. If you're running a kind of millions and millions of steps, you do run into memory problems again. So the method I'm kind of proposing to get around this is called reversible simulation. It's been studied in other contexts, but not in the molecular simulation context. So the motivation is, look, we use AD to take derivatives through complicated algorithms, right? But a molecular dynamic simulation, as I showed in the first slide with the discretization, is actually not super complicated. You're doing the same thing over and over again. We also use AD. AD stores intermediate states, right, to allow its accumulation backwards. But molecular dynamics is actually reversible under certain conditions. So do we actually need to store those intermediate states? And can we replace the whole computer memory overhead of reverse mode AD by actually just deriving the same thing symbolically? Maybe a bit of a heretical thing to say at an AD conference, but there is a slight technicality that for the Langevin case, you do require, you do need to run the forward simulation and record the noise. But if we think about the mass of this, so if you're calculating the derivative of the loss with respect to the parameters symbolically, then you use the multivariate train rule, and you have to give the partial derivative of kind of each contribution. So the first contribution is the contribution from the loss function itself, which is the first term, which you can calculate once at the end of the trajectory. And then at every step, the parameters contribute via the force function f, okay? So you then need to sum up these two terms, basically, and you can accumulate the LDF term at each step. So this is what reverse mode AD is basically doing under the hood. And then you can also extend that to a case where you take loss values periodically, in which case it kind of becomes an average. So I started to do this manually, and it was real pain, and I kept running into errors, so I used symbolics, .jl, which is a lovely little package which can take these gradients for you, and so you can derive it. I've just put two terms up here. They quickly kind of grow in complexity. But the crucial point is just that each term can be constructed by adding to the last, okay, using a series of accumulation values. And also, there's something interesting here about explosion. In the Verlet case, which is when gamma is 0, this leading term goes from 2, 4, 6, 8 as you step back through the simulation, and that shows what is known practically and what I mentioned before, which is that the gradients do explode. Okay, so that kind of is shown in the maths. For simplicity, we're kind of using a case with just one loss value and no velocity, and velocities in the loss, but it can be extended to those cases quite happily. So the actual details of how you do this with accumulation are not super important. They're up there. You need a series of accumulators to track the intermediate values. The key part is that there are 2 gradient calls required here, which are shown in red. Thankfully, they are vector Jacobian products, so if you want to use AD, they're very efficient. And in simple cases, you can actually explicitly code these as well. one complication for machine learning potentials is that one of these gradients, you do need the derivative of the force with respect to the coordinates. Now, the force itself is often taken as the derivative of the energy with respect to the coordinates. So you would actually need higher order AD, but that is often very achievable in something like JAX and even in Julia. Okay, so let's try and compare this to what we saw before with force balance. So this is the reversible case I've just introduced. And then earlier on, I mentioned the ensemble-based case, which is the kind of differentiable force balance. And we can see the correspondence of what we're actually calculating here. The first term is how the loss responds directly to the parameters. And in the second term is kind of how the weighting of the states changes as the parameters change. And it's just two different ways of doing it. One is explicitly through a simulation, and the other is via statistical mechanical weightings. We can also compare to the adjoint method. So it actually looks very, very similar to the adjoint method. So the DLDFI term I introduced is analogous to the adjoint, and the DF d sigma term I introduced is analogous to the kind of more general DF d sigma term from the adjoint equations. And if you compare two of the kind of adjoint terms, as I'll call them, with an Euler discretization for the adjoint method, they do look somewhat similar. However, they are actually fundamentally different. They are solving slightly different things because we are discretizing before differentiating, whereas the adjoint does the opposite. And there's been some discussion on why that might be useful. So we implement this using Molly, and enzyme and zygote. So I spoke about Molly last EnzymeCon, so I'm not going to talk about it here. Currently, it's set up to use reverse mode AD, which I introduced earlier, and it uses zygote to do that with enzyme for the slow bits. It's going to switch, so when enzyme gets support for kind of general GPU array programming, which will hopefully be soon in reverse mode, then we can switch to using enzyme through the whole thing, which would be really nice and allow us to write really fast non-mutating code. However, for the reversible simulation case, which I just introduced, the gradients are only required within each step to calculate the two vector Jacobian products. And currently, you can do this either in enzyme for something like a machine learning potential, or even explicitly write out the gradients in simple cases, in which case there's no automatic differentiation at all. So to test this, we look at Leonard-Jones simulation. So, look at a simulation of water. So you just imagine kind of 900 water molecules floating around in a box, and they interact using four kind of components. The covalent bonds between the hydrogen and oxygen, and the bond angles keep the correct covalent geometry of water. And then we have a Leonard-Jones, which is a general attraction-repulsion term, which has two trainable parameters. And then we have a kind of Coulomb charge term, which has one trainable parameter, which is the oxygen charge, which also defines the hydrogen charge. So this kind of simple system, which is defined by, in our case, three parameters. And so I won't go into the exact details of the loss function. We use radial distribution function, which talks about the distances between things, and entropy of vaporization, which is based on how much energy it takes to evaporate something. So I mentioned this is the reversible approach is identical to the reverse mode AD approach mathematically. So the difference between them ideally should be 0. Of course, in reality, you have numerical error. We find that the percent difference at one step is basically numerical error. Numerical error is very small. As you take kind of 10 steps or 50, 100, the error does increase, but it's always much, much less than 1%. They're effectively the same error, same gradients. In practice, we actually truncate the gradients after about 200 steps. I kind of alluded earlier to why we might do that due to explosion. Just to show that explicitly, here's plots of the loss value on the y-axis against the gradient of one of the parameters on the x-axis. And ideally, of course, the loss should be minimized when the gradient is minimized. And we see that that's the case for particularly the 200-step case. As you go beyond 200 steps to 500 or 750, we do see gradient explosion, and the gradients are no longer useful. I also mentioned, we can do all this with force balance, so we can look at correlation between the two. And actually, when I was looking at this correlation, I was really surprised at the strength of the correlation between the ensemble-based and the trajectory-based methods. If you set these methods up well, they basically give you exactly the same thing, which is encouraging because they should do theoretically. However, we do see one potential advantage of the reversible simulation. If we look at the kind of gradient variance, so this is, you repeat the same simulation, you calculate what should be the same gradient. Of course, you have different starting coordinates, etc., so there's some variation. And we see that there's more variation in the differentiable force balance case and less in the reversible simulation case. So this is perhaps some early evidence, and we're obtaining more evidence, but this is early evidence that the trajectory-based approaches could actually be more accurate. So if we try and actually optimize these parameters, in this case I mentioned there's 3 parameters, but in this case I've just shown 2 for clarity. We start off from a whole series of values all over the plot, and then in red is shown the kind of final point, the lowest loss point, and we see that the reversible and the differentiable force balance case basically converge on the same kind of region of space, which is what we expect. And this was done using optimization.jl. And then similarly, we can do exactly the same thing with a different optimizer and see that this optimization is fairly robust. So how does this work in terms of performance? Well, there's a few different complicating factors. The cost is one forward simulation, followed by the kind of same thing backwards, if you like, so the reverse simulation, similar complexity, plus 2 reverse mode equals that I mentioned before. However, in the molecular mechanics case, those gradient calls are actually fairly simple and can be explicitly coded. In that case, there's no automatic differentiation at all. Everything's purely explicit. And I also mentioned that we need to clip every 200 steps. If you take the loss every, say, 1,000 steps, which would be typical, this actually means you only need to step backwards for about 1/5 of the steps. So in practice, once you weigh up all these factors, it's roughly equivalent to reverse mode AD through the whole simulation, but with the crucial difference that you have low memory overhead. So to sum up, here are the kind of all the different methods and the pros and cons. The numerical methods tend to be scale poorly in the number of parameters, and they can be slow and a bit inaccurate, but they do work, and they've historically shown success. The ensemble-based methods are, they're very principled. They're based on statistical mechanics. They work well, but they do have limitations on loss through multiple states. And then the trajectory-based methods, which are a bit newer in this context. The adjoint method is, again, it's kind of very principled, but it's sometimes unclear how to discretize the equation. Reverse mode AD has this prohibitive high memory cost, and hopefully the method I've introduced today, although it's untested, and you would need to implement it currently, I think it's very promising. And just kind of final motivation about why we want to train on all these things. Well, we want to target all sorts of things we can observe in the lab. We want to match them on the computer. So, you've got protein-protein interactions. I mentioned radial distribution function already. Flexibility of proteins. In the pharmaceutical context, you have protein ligand binding. You have phase changes and things like fitting to experimental data as well. So thanks to George Shear's group at the LMB, who I kind of sit with and help me. Thanks to all the Molly contributors. Thanks to the many Julia contributors and package authors, including Billy and Valentin, who have been very helpful in fixing lots of enzyme bugs. Thanks to Enzyme and GrowMax, OpenMM and GrowMax, who have been a heavy inspiration on Molly and a lot of the work done here, and to our computing resources. And again, I'll just mention we do have a postdoc position open, so do come chat to me if you're interested. Thank you for your attention.
Thank you, Joe. Are there any questions?
How does it scale the number of particles, like how many particles, and how does your number of steps will influence that decision?
Yeah, so it would scale linearly with number of particles, which is the same scaling as standard molecular dynamics, which uses a neighborless scheme.
So suppose if I take larger simulation, would it be beneficial to reduce number of time steps in a single step trajectory that I will take, or I can take say number of time steps in a trajectory?
Yeah, you can take any number of time steps. There will be a trade-off it depends how long the loss value you're calculating is exhibited on. So for instance, if it's water and it would relax on the course of picoseconds and it would lose all knowledge of where it is, then you could simulate for picoseconds, and you might be better off repeating that kind of 100 picosecond simulation multiple times. If it's something like really long, like protein folding, which takes milliseconds, you would obviously need to simulate for more to see that. So it depends on the observable quantity. Yeah.
Okay, and what about simulations such as grand canonical simulation or Monte Carlo?
Yeah, okay, grand canonical. So grand canonical, for those who don't know, is where you add or remove particles. So I think that can be done. Yeah, the way you would do it is using you kind of set up buffer memory and you would pad it basically. But I think that could be done. I haven't derived the maths. Yeah.
Would they follow the reversible principle properly? Like if suppose if I take some sort of Monte Carlo optimization, I'm
I don't know about Monte Carlo. Yeah, I think Monte Carlo wouldn't know because in Monte Carlo every state is there's no kind of a differential equation you're solving. It's more a sampling method. You can use Monte Carlo for the ensemble-based methods. You can't use them for rejection-based methods. Yeah.
Last question, please.
Yeah, maybe a question that I thought the checkpointers would ask. This high memory cost in the reverse would can of course be mitigated if your checkpointing is not just the memory but file also.
It can be. Yeah, I think. So I've used it extensively for the work here, and it definitely can mitigate this. The problem is for this work, which is heavy checkpointing. The problem is if you have a machine learning potential and you're running a GPU, for instance, you might only be able to keep a handful of evaluations, and so you might need to checkpoint every single step, which is still possible. But even if you're doing it on disk, that's a disk write and read every single step. And so you then convert the memory problem into a runtime problem.
And did you look into Revolve?
No, I mean, so all these methods mitigate it, but if you're using, but they do put a limitation on the size of the neural network you can use. Yeah, I think.
And the GPUs that you use are having how much RAM in?
I mean, it depends on the size of the system. If you have we have large GPUs, but if you have a 1 million particle system and you want to run a graph neural network on it, it's still going to take up a decent fraction of the.
So you use 32 gigabytes.
Yeah.
Better.
Okay, let's thank the speaker again. With a slight change of plans, the next talk was supposed to be Joseph Camp, who could not be here, so Patrick and Billy volunteered to step in and still talk about EnzymeCon, is it right?
Okay. Hi everyone. Joseph Kump was supposed to give this talk, but he had a family grievance, so he sends his regrets. He wished he could be here, and so I'm going to try my best to give a quick overview of the progress that he and team members that are listed here have been making on differentiating an ocean general circulation model in Julia. And I was going to take the opportunity to actually give some sort of high-level introduction of why it is and the different reasons of why we are interested in using gradient information in oceanography. And the same for something similar applies to, of course, atmospheric sciences. So in the ocean, we have a very sparse, heterogeneous, patchy observing system, very few observations in the interior. Of course, we can simulate the ocean state using LES simulations, but that's, of course, a simulation. It's not observations. really stick to observations where I have a sort of a highly undeterminate system. And on the other hand, we have numerical models that also require uncertain inputs or parameters. And so the goal is, well, it doesn't work, okay. So the goal is that we want to learn from the most complete set of available observations in the ocean or simulations and known physics that's encapsulated in the equations of motion by solving basically like either giant least squares model data misfit problem. And for that we use the adjoint or Lagrange multiplier method. But so I wanted to here in the context of oceanography, so what do we actually mean by learning, right? So we have this a physical model, or let's say the blue here is a dynamical core of a model. And that model needs uncertain inputs, right? It needs initial conditions that are uncertain. We don't know the initial conditions when we start the model, the ocean state, let's say in either in the 1900 or in 2000 or anything. They're uncertain. We force the model with surface boundary conditions, the atmospheric state. That is again uncertain, even if we use the best possible atmospheric fields that we obtained from the numerical weather prediction centers. They still have uncertainties or errors. And then we have model parameters. Actually, well, this still doesn't work. Okay, I'm just going to leave it. So in model parameters, these are subgrid scale parameterizations of things that we cannot resolve with the numerical grid that we have, or the empirical, even constitutive laws, for example, due to viscosity, that we just are empirical and for which we don't have the right functional representation. And so let's look at these in turn, right? So, for example, we want to learn the uncertain boundary conditions. Let's start with something sort of that we don't necessarily think about. So we have, for example, observations of interior tracer fields in the ocean, and what we do not know that was uncertain is actually what are the corresponding ASC fluxes that lead to increase or decrease in these tracers. And so basically what we have here is the inversion for fluxes. Another application, of course, that's the one that's sort of the more conventional and the standard one, is that we have the uncertain initial conditions that we, for example, want to optimize for optimal forecasting. And so the optimal forecasting problem here is a filtering problem. We have in red this trajectory forecast, and then we come to a point here. These are the black crosses. Then we have observations here. These are the blue circles. And so basically we want to get a sort of a new, what the forecast people call an analysis that basically gives us the optimal initial condition to basically provide our next forecast. And that's a filtering problem. One of the ways on how this is solved, for example, ECMWF is the 4D VAR problem. But we also have the smoothing problem, which is we want to actually learn sort of the time evolving states. So that's a reconstruction problem. So unlike the filtering problem, that's a smoothing problem. And so here, what we have here is in blue, we have observations of the state at individual times. And so we want to basically have an optimal, use the model as sort of an optimal smoothing. And again, we adjust everything here that's in red in order to basically get an optimal trajectory. And here, this trajectory are not the red lines here, but they are actually the blue line here, where we basically try to conserve the equations of motion exactly. And so that's this blue dotted line here, unlike the red lines here for the filtering problem that give us these analysis increment, and these are unphysical updates at all the periodically whenever we perform an analysis. So the reconstruction problem here, in that sense, is different from the forecasting problem in that we preserve exact dynamical and kinematic consistency. So over the entire time period that we see here, we follow the equations of motions exactly. Then the next thing here, we want to actually learn not the initial condition or the boundary conditions, we actually want to learn the parameters, because that amounts to basically a model calibration problem. And of course, it's a big topic also in climate modeling or in even ocean or atmospheric modeling. So where we have uncertain parameters, for example, again, for all of the subgrid scale parameterizations, and then trying to basically, how do we use data in an optimal manner in order to have a well-calibrated and non-biased climate model. And in some sense, that is in some sense the problem that the CLIMA, the Climate Modeling Alliance, is tackling, unlike the previous ones that maybe are not of immediate interest, maybe not immediate interest to the CLIMA problem. So this is really sort of gets to that application. And then the next application here is where we say, well, we actually don't quite know the functional form of these parameterization schemes. And so why don't we just replace one of these parameterization schemes by a surrogate model, for example, a neural network, right? And so then there's these two approaches, the one that relates to what's been called offline learning, that basically tries to say, well, we basically pre-train a neural network using, for example, LES simulations, and then we plug that sort of trained neural network into the full model. And there is no guarantee necessarily that that basically solves all the problem, and therefore the idea is to basically train the neural network within the full model itself, for which you then basically have access to also other variables that or parameters that you might try to optimize, and that sort of goes under the notion of full model or online learning. And actually Sarah Williamson is going to talk more about this in her presentation tomorrow. And the point of basically this overview is that we can, and we have, or yeah, we can use gradient information for all of these applications, right? And so I want to really point this out, that there's a wider class of applications beyond just sort of the pure parameter optimization problem that oftentimes is sort of the focus on. Is for all of these, we can actually use adjoints when we talk about inverse problems or data assimilation, or in the context of neural network training when we talk about backpropagation. And so this idea of sort of this end-to-end model learning is kind of what we're after here with this using the differentiable programming, and that's the content of this project, an NSF-funded CSSI project that we call the DJ for Earth, the differentiable programming in Julia for Earth system models. And the key sort of work engine here is Enzyme and also checkpointing, so enzyme.jl and checkpointing.jl, and you see some of the protagonists here, so I don't have to mention that. And the initial applications here are on sort of what we sort of the focus applications are on an ocean general circulation model, and then in connection to that a sea ice model, and then also an ice sheet model. And we have Chenggong here, who is basically together with Mathieu Morlighem working on this problem. So let's now dive into the ocean application. So this is a slide that I've borrowed from Raffaele Ferrari here at MIT. And that is basically the ocean model. It's the goal of that we'd like to differentiate. It's oceananigans.jl. It's written in Julia. It runs extremely fast, and Simone Silvestri here in the audience is one of the core developers here who can tell you all about this. He has a paper on arXiv on some of the performance gains here that are quite stunning, I have to say. So it's really a very exciting new way of basically simulating the ocean on extremely efficiently on GPUs. And that's basically the target application that Joseph has been looking into. This was supposed to be an animation. Unfortunately, I did not get the animation for this, so I just basically a static here, just as a still, an idealized Antarctic slope current configuration with sort of an idealized initial sea ice thickness distribution. And then at two different resolutions, you see at the top, well, you actually can't see it, but if you were to see it at the top, you could see the coarse resolution evolution of this state, and then the bottom is the high resolution configuration. And so the work here is yeah, okay, it's an idealized as from what I understand from Joseph, that's what he was trying to simulate here. So the structures that Joseph has basically worked through in the context of enzyme. Everything here in this blue box, so there's sort of the grid that he's been looking at is sort of right now sort of just a rectilinear, apparently not yet a longitudinal grid, and then I understand that oceanarians are also in the process of implementing a cubed sphere grid. From the model itself, everything that's here is underlined are pieces of the code that he has been exercised in the contents of enzyme, and also by so inversion means that so everything that's not underlined yet is basically in work in process. And in particular, so what we can summarize here in this picture is that what has not been differentiated yet is basically all the terms in the momentum equation. But what has been done is basically we are able to run a simple advection diffusion problem in the context using the Oceananigans structure. So that's kind of the summarizing the different pieces of this box here. And so yeah, so this is again sort of the progress here. So successfully differentiated the grid, and in fact the grid itself is, unless you use some sort of a z-star coordinate system, the grid is currently enforced to be inactive. We have the velocity field so far prescribed, so it's not a prognostic field, but it's a prescribed field for to do the advection diffusion problem. And then of course the conservation equation for heat, basically the temperature equation, and I think also the conservation equation for salt, and then basically the tracer advection. So some of the tracer advection code has been differentiated. Then a lot of work that Joseph spent was on improving type stability in most parts of the Oceananigans code base, generalized enzyme rules for tuples, and then also extended AD rules for the kernel abstractions, which was also it's sort of a major work. And then as an initial application with what we have now, again, it's still not really an ocean model because we don't have the momentum equation in the mix yet. That's being worked on now, but we can already think about sort of as a proof of concept example in the context of the trace and advection diffusion problem is that we could, for example, invert for initial condition, and that's what Joseph has begin to set up. So we have sort of a bounded idealized domain. It's a prescribed constant velocity field, and then we use a tracer advection using the Wino advection scheme, vertical scalar diffusivity, and then basically running here. So you run this problem here, you run the forward problem. That's this upper box here. Then the lower box here is you have a misfit function, so where you basically compute the interior simulated the tracer field that is here in this context a passive tracer field. So it's not temperature or salinity, it's just a passive tracer field that does not affect the baroclinic structure of the flow field. And then basically you use enzyme to compute the gradient of the misfit with respect to the initial condition to then recover and sort of the correct initial conditions from the advected and diffused tracer field. And that's basically the work that's shown here. So to conclude, the ongoing work on the technical side is to add continuous integration tests for enzyme to the Oceananigans pipeline to streamline the testing. And then, of course, the next step, so this is formulated, what Joseph formulated initially is basically inverting for the initial conditions, but the more exciting part in this specific context would be invert for the surface boundary conditions, so for the tracer LC fluxes. Then differentiating actually the full simulation struct. So right now the time stepping is basically a handwritten time stepper. It's not using yet the simulation time stepping that's basically comes with the Oceananigans itself. That's a work in progress. And then of course the differentiating the momentum equation as to basically really go into something that's close to the full Oceanigans model. And then, of course, there's a number of science applications that are basically on the horizon, and those are exactly the ones that I've showed prior to going into some of the technical details. And so some of the references here in the context of what we've talked about. This is where you find sort of Oceanigans on GitHub, and also some of the EnzymeCon's work. And so I'll leave it at this, and happy to take questions, and also hopefully leave a bit of time for Billy, who also had sort of 5 minutes that he wanted to use.
We will be over time. Thank you.
Any questions?
I have just one comment. I think that this work is very similar for the fluid dynamics with the Chopin's model tuning, and actually we also do the similar things like try using not this, but using neural network to enhance the current Chopin's model, and using action method to learn from the LBS, etc. So to improve the best model, and there's quite some similarity in this work. We also do the offline training and online training. So I think it's a very similar work here.
Yeah, it's totally similar. And in fact, in the atmosphere, we've been sort of scooped already by atmospheric people. They're always a step ahead of us. So there is some work that Google has done where they actually have differentiated an atmospheric model, and sort of with some sort of similar ideas sort of that we'd like to implement here.
So I think the same experience can be shared with the different areas.
Yeah.
Other questions, comments, please?
Do you know, like, differentiating through the parts of Oceanigans that were already underlined, which ones were like the components that were more straightforward to do this from a technical point of view, and which ones were like the ones that are like things but
Yeah, so I think, so that's actually a question. So I have not had my technical hands on here. This would be a question, mostly Joseph would be the best to answer, but the second best would be the people who helped him with this, with our Billy and Valentin. But I think, and on this list here, actually on this list here, it seems to me that really some of the last 3 bullets even, so improve type stability for portions of the code, generalized enzyme rules for tuples, and then the kernel abstraction. So these were 3 of the critical element to even do anything, to go into actually the physical sort of. So is that correct?
Yeah, so basically expanding on that a little bit, so specifically Oceanigans sort of extended and sort of casually broke the kernel abstractions sort of rules, saying that, like, I'm going to define this grid type and abuse the starting variable to represent an offset, which meant that someone else who looked at the kernel abstractions definition had the wrong bound sizes because it was like this variable was misused. We've since fixed this, and thus this have it resolved. Similarly, there's Enzyme, at least a couple months ago when we started the work, didn't have as good support for sort of type unstable code, and we resolved this in 2 ways. The first of which is we made Oceanigans more type stable, which also just makes it faster, which is good generically, and then we also have been extending Enzyme to handle more type unstable code from Julia, so hit it from both ends, so to speak.
Thank you, Patrick.
Yeah.
Let's switch. How much is this Oceanigans or EnzymeCon or any of that?
Yeah, this is just another related thing.
Yeah.
You'll be in about 10 minutes or so. Okay, cool. So this is second talk. Sorry, this is the second talk in the slot, and it was slightly prepared during a previous talk, so please apologize if things appear to animate when I did not expect them to animate. So this represents ongoing work on the Enzyme JAX project between myself, Alex, and several other folks. So to begin with, we had a good intro a little bit to JAX earlier from Dougal yesterday, but just as a quick refresher, so you have NumPy in Python, and JAX sort of gives you a NumPy style API where you can write code, except now by virtue of running through JAX's, or technically XLA's JIT, you can, as a consequence, fuse operations together, run on GPU, TPU, whatever else you like, as well as use JAX's built-in automatic differentiation. Now, notably, JAX's AD is really great. Sort of, you can imagine doing jax.grad. It takes in a function, spits out another function. However, it does, like Dougal mentioned, come with a little bit of a caveat that all of your code needs to be written in the sort of functional or JAX-specific subset of Python. One neat thing that we've been doing relatively recently is, so we have an extension package inside of Python that lets you import arbitrary external code, in this case C++ code, into JAX as an arbitrary layer. So if you have, say, an application which doesn't fit with the traditional form of functional Python and you want to import it, and more interestingly, because this is EnzymeCon, get the derivatives of this external code, we will provide those derivatives as, using, in this case, enzyme automatic differentiation for whatever your foreign code is. Currently, this is only implemented for LLVM, MLIR, C++, but any relevant language, if there is desire for syntactic sugar, we can add to and, say, import Julia code as a middle layer inside of JAX, as an example. So another interesting thing is, JAX fundamentally is just talking about Python's IR. Enzyme is a compiler that takes IR and gives you the derivative on it. Can we just differentiate JAX itself in addition to injecting other code into JAX from another source language? So to talk about this, let's look a little bit at the JAX pipeline. So we start with Python. It goes to this JAXPer IR representation, and then eventually goes down to a sort of XLA-specific MLIR dialect known as stable HLO, and eventually to LLVM and to binary. So looking at this a little bit more deeply, if we talk about this, sine of x squared, and we want to look at the grad of it, the JAXPer, which I'm just going to glaze over a little bit here, which is the sort of like internal IR state of JAX, is now shown here on the right. One thing which is actually very explicitly highlighted here is there's a bunch of code that is not actually necessary. Like as an example, we have that sign, and we're not actually returning the original sign, so we don't need to compute it. And there's similarly a bunch of other pieces that are fundamentally no-ops or otherwise things that we would want to go ahead and optimize. Now, this sort of demonstrates that this JAX level IR can benefit from the usual style compiler optimizations both before AD, as we potentially showed earlier, but also after it. Unfortunately, all of those optimizations right now, to the extent that they're there, exist only after all of the JAX has been lowered into, say, LLVM IR, as an example. So specifically, JAX doesn't just directly lower down to LLVM IR. It actually goes through multiple levels inside of a slightly higher level framework called MLIR, which is in the same monorepo as LLVM, except now has not just operations for the add and multiply instructions in LLVM, but you can define a custom operation for whatever thing that you want to represent. And this particular dialect, which is what JAX directly lowers to, which is being shown, is something called stable HLO, which effectively has high-level matrix math like transpose, multiply, etc., in addition to a couple of these other pieces. Now, ongoing work, again, that has been the result of myself, Alex, Jacob, Martin, and several others, has been extending Enzyme to not just differentiate native LLVM, but arbitrary MLIR compiler constructs as well. So the idea here is we could similarly take in the stable HLO, as an example coming out of JAX, directly differentiate it, and imagine looking at what we can get out as a consequence. So once again, if we look at that original JAXPer, we have all those optimizations that we would want to perform. Unfortunately, they aren't really performed in the JAX level IR. The hope here is, could we, by putting it inside of a compiler, now optimize this intermediate representation instead? This leads us to step 3, actually combining JAX and Enzyme together, at least for the automatic differentiation sense. So once again, we had our earlier picture where the JAX level IR goes down to stable HLO, goes down to LLVM. However, if we actually want to go and differentiate this at least with the original version of Enzyme, so the first Enzyme paper was actually to apply automatic differentiation right at the LLVM level.
But the sort of Python that comes in is much higher level. It's that sort of functional form with all those array style notations. Of course, we can still apply AD here, and this is a question as to whether or not it is better to apply AD here or at another level. But if we actually dive in a lot more deeply, JAX doesn't just go to stable HLO then to LLVM, it actually goes to stable HLO. Then within the MLR compiler, there's a ton of different dialects. We have that super high level functional form, stable HLO. You have a linear algebra sort of layer that imagines a generic form of all of these sort of matrix ops that you want to do. Eventually you have loops, eventually you have control flow graphs. So there's actually, and this is probably a good point of discussion, very much to Jan's earlier discussions of which level of abstraction is the one that we want to specifically go for. So in trying to talk about this question, we've done some sort of early stage experiments to see what we can do with what we've done at the moment. So specifically, rather than trying to just define the individual assumptions that only these IR pieces exist, the question is, can we extend it now to support differentiating an arbitrary construct? And then any person can go ahead and say, hey, I want to differentiate this LVM IR instruction, or hey, I want to differentiate this lineage instruction. So we can imagine not just supporting differentiating whatever both existing and new IR constructs someone can introduce, but also we can imagine deferring some of these pieces. So perhaps it makes sense to differentiate some pieces at the high level, but wait for others until a lower level. Specifically, because we want to make this as easy as possible for people to define their derivative instructions, we have this high-level sort of table gen form of defining the derivative operator. So in this case, we're defining the derivative for the divide instruction. We say that the derivative with respect to the x, or the numerator is in this case the derivative of the return divided by y, and similar for the derivative with respect to the second argument. Optionally, if you want to define a different derivative from the reverse mode versus the forward mode, we support an optional form of saying, here's the forward mode derivative in contrast to the original reverse mode one. But if you don't specify it, it will auto-generate it by summing up the individual pieces. Some of the benefit of this sort of like DSL table gen form is this will automatically give you the derivative for all modes of enzyme, all variants of it. So if you're someone who's been staring at Julia writing all the enzyme rules, one of the benefit of this style internal approach is such that you write it once and it gives you every single variation that you can imagine needing. Where we are right now, so currently we've implemented using that style of table gen talked about earlier, the combined forward and reverse mode rules for many of the common MLIR dialects. In this case, stable HLO, arithmetic, structured control flow, or SCF, affine, which is a polyhedral style form. And specifically, this has been enough at least to run some ML models. Again, the original enzyme hypothesis was that by combining optimization with automatic differentiation, you can yield potentially better results than running AD in isolation before any of those optimizations apply. Naturally, now that we have these derivative definitions implemented in all of these areas, a natural question is, can we evaluate the similar hypothesis, and does it now hold not just at the LLVM level, but at the optimizations for the matrix math, or the optimizations for the loops? We went to go and evaluate this, and unfortunately found that there were no optimizations implemented for a lot of these matrix things, at least in stable HLO. For example, saying that the transpose of a transpose is just the identity, things like that didn't exist. So we went ahead and started implementing them. The early work that we have so far supports the enzyme hypothesis, specifically taking those optimizations that we have now also built, at least for the matrix level, does yield better performance than just running it originally. But once again, these are generic optimizations that aren't just helpful to AD. You can just take these optimization passes, apply it to the regular code out of JAX without anything to do with AD, and it'll also speed it up because optimizations generally try to improve program performance. I unfortunately don't have a plot talking about the early performance examples, mainly because this talk was written during Michelle's talk. I'm so sorry, Michelle. But happy to talk more about specifics during the break. And like I mentioned, there's a ton of open questions, including, now that we can imagine looking at the level we want to apply AD, where do we want to apply AD? Do we want to defer some of these pieces to different levels, not just do them all at once? What optimizations do we want to add and which ones are actually helpful, and a ton more points of open discussion. Thank you so much.
So
But given all that, though, wouldn't the enzyme hypothesis in the end just mean that doing it at the LLVM level should end up being the best, like at the very, very end of the pipeline after all optimizations, or?
So not necessarily. Like being able to apply a ton of optimizations first is definitely beneficial, and why, you know, we've now applied all of them. Historically, doing it at the LLVM has been the best. The caveat to that, right, is there's some styles of optimizations that you want to run both before and after, and also not just sort of run them all before, but combine with optimization. A good example of this that we talked a little bit about yesterday was in the context of scheduling. So if you say have a parallel for loop and, you know, reads become writes, what previously may have been the perfect schedule for your original code may not be the perfect schedule for your reverse code. So working at a stage where you can do optimizations that sort of change how that parallel structure or schedule is done would be beneficial. Of course, there exist such schedules on the LLVM level, but this is mostly a matter of now discovering where these optimizations exist and how we can sort of fuse them together with AD and not have them be completely isolated components from each other.
Other questions?
This might be sort of like a really naive question, but can similar analysis be applied to Python? Because I remember original enzyme paper also had similar analysis about Python and for torch scripts to be more specific.
Yeah, so the sort of import C++ style example into PyTorch, same style thing, equally applies there with respect to taking the PyTorch input code and using Enzyme to differentiate it instead of PyTorch's native differentiation. Actually, PyTorch does have a backend that directly goes to the same IR called stable HLO that JAX goes down to. So the same infrastructure could be once again used here to differentiate those pieces. PyTorch also has a different backend as well that you can pick, but you can imagine doing that setup. And actually there's some folks who are specifically very interested in that, but we haven't had time to go just do the syntactic sugar combining the stable HLO that is the inside of PyTorch, at least in that backend, with the PyTorch syntactic sugar. So if this is of interest to you, we have a bunch of folks who are also interested in that we should just set up a meeting together for.
Last question.
So maybe this was, I'm wondering if you encountered cases where you had to differentiate at a higher level to correctly encode the semantics of the program specification. So that'd be like, I don't know, if you have sign, you might have Taylor expanded, and then the LLVM level might be expanded. You might want to do that at a higher level. I'm wondering, is that part of the motivation, or is that just not relevant? And if it is, what are some examples?
So at least if we look at code coming from JAX, we've never had that as a limitation, mainly because, right, LLVM has a sign instruction. So for all of these pieces, there is usually an LLVM intrinsic that corresponds to it. So there's not a need from that perspective. Ironically, coming from C++ code or other pieces of code, there is a similar sort of thing where people have written bit hacks or Taylor series expansions to sign and so on. The way that we usually resolve this is we say, you know, write a custom rule, or in C++ we have some nice syntactic sugar that says this function behaves like sign. You don't need to write a custom rule, just we assume it's sign and we can do all the things on top of it. It does somewhat vary based off of, you know, like what the primitive set of your programming framework is, but at least coming from JAX we haven't seen the need. Coming from other programming languages we have.
Thank you, Billy.
I don't get to roam around.
You need to stand in front of them.
All right, cool. Yeah, I love to use the stage presence though. All right. All right, so no musical today. Cool. So yeah, so you know, I think I'm very happy to be here at EnzymeCon because I think, you know, of the groups that you're using Enzyme, I think that we could probably have the claim of, you know, being some of the early power users and really kind of driving a lot of why, you know, a lot of, like, you know, I think we found a good use for Enzyme really early. And so I want to start with, you know, why we find Enzyme to be very useful, but then also what the heck we're trying to do with our big organization and why this is something that is important for the enzyme ecosystem itself, right? So I want to, I couldn't find what the right way to start this talk was, so I kind of thought, let's go find some claim in machine learning, and let's see if we can kind of talk about it in some detail to be able to see why different automatic differentiation libraries matter, right? So here's one from a researcher that I really respect. This is Paris Pardiakaris' lab, this physics-informed deep O-nets, where they make this statement that, there is these new machine learning methods that solve differential equations with neural networks, and outperforms it, at a fraction of the cost of all numerical solvers, right? So everything I've ever done in my life is doomed, right? Everything with the numerical solvers, every ODE solver we've written, it all doesn't matter, right? So then you take this paper, right? You take their code, you implement it in Julia, and you realize that, oh wait, the numerical solver that they're using was just about 10,000 times slower than the Julia ones, and that completely changes the results from the machine learning method is faster to now the machine learning method is now a few orders of magnitude slower than the ODE solver, right? They updated their paper. It's a very respectable researcher that really took this into account and everything, right? But I think that the question that you should really ask is, how did this happen? Why did this happen? And why is the machine learning community, how could this show up in a machine learning paper, right? And I think it's a really important question because a lot of people would just say, oh, they messed up here. And I don't think that that's the case, right? What instead happened is the fact that machine learning is so much easier to optimize than scientific computing code, right? Because if you're working with big neural networks, then you have a lot of these O of n cubed operations. And so things like manual memory management, do you allocate a new vector? Oh, that's just O of n. Do you do SIMD here? Kublos is doing all your operations. And everything's just a big neural network on the GPU. And so what we find is that for machine learning codes, the difference between knowing what you're doing with machine learning codes and not knowing what you're doing is like at most 3x, right? Like just taking your big neural network and putting it on the GPU and using kublos is 90% of what you need to do, right? But that is not true for scientific computing, right? When you're doing these scientific computing codes, you have, sparse matrix operations where you only want to loop over the non-zeros. You have all this nonlinear mutation going on and everything. And these kinds of codes are much more difficult to optimize, right? So I look at that result and kind of say, it is actually an issue due to the fact that, the way that we're doing scientific computing, it's much more in the weeds with the numerical implementation, and a lot of AD libraries do not really take that into account. They just kind of say, use as much linear algebra as possible and we'll be good. And that is great if your entire pipeline is just linear algebra, which is machine learning. That's why it became popular. But when we start to do scientific computing codes, that assumption goes out the window. And who do we call? Enzyme, right? So that's really why we kind of started going to enzyme, right? It had this really big focus from the start that mutation and all these kinds of things that we do in scientific computing codes, they matter. We're not just going to throw them all out. And so it became an AD library that we can really kind of work with in a sense where it would match the code style that we would see in our libraries, right? Which, again, is a code style that is very different from a lot of machine learning kinds of operations. Now, to really show this, I want to talk about differentiating, my favorite subject, differential equations, right? So how do you differentiate an ODE? Well, at a high level, it's kind of a three-step process, right? If you solve an ODE, U prime equals F, what you do is you generally solve a different ODE going backwards, and then some integral based off of that, and that gives you what your derivative is, right? So basically, the derivative of an ODE is solving another ODE. It turns out that even differentiating a solver is going to be differentiating another ODE. We'll come back to that in a second, right? But so generally, solving ODEs is something where there's a continuous thing, and we want to be able to differentiate a continuous object. And now the way that people actually write their code, right, if you look at the top there, the key thing here is that there's a lot of scalar indexing and there's a lot of mutation, right? So, if you're doing things with like a neural network inside of there, the neural network is linear algebra. And yeah, if you're doing things with a PDE, maybe you multiply by a sparse matrix. But when you write down these nonlinear operations, people are doing things like U of 1 times U of 2, like you're writing down a very specific nonlinear code, and you don't want to be making tons of small vector allocations and all that. So, you're mutating vectors and you're reusing as much memory as possible. You're doing a lot of manual, SIMD operations and such. All of this matters, But then we have this chunk of code that we have to actually have to differentiate if we want to use the adjoint method, right? And so this should actually puzzle a few of you, because you might know, for example, that Julia's zygote library is one of these machine learning style automatic differentiation libraries, and so it doesn't support mutation. And so what I do is I take this ODE that is defined with mutation, I put it inside of a loss function, I call zygote, and it works. And you should go, wait, I thought you just said it doesn't support mutation, you're differentiating a mutating code. And it's like, exactly. We've been doing this for years. For years, we're putting enzyme on people's codes when it doesn't show up in their example. So what is going on here, and why are we doing this, right? So the key here is that we've done this in a solver-independent interface, right? So what we say is, you define an ODE problem, and then you solve an ODE problem. That solve function is dependent on the problem that you give to it, but also dependent on the ODE solver. And there are keyword arguments, which are optional, by the way, for how you actually do this differentiation process. And so the core design here is that we, instead of saying, oh, we're going to differentiate, these specific solvers or things, we differentiate problems, right? An ODE is something that can be changed from, solving the ODE forwards to this process of calculating the derivative, and we can set it up so that way for all solvers, we can have one piece of code that generates that process, right? Now, so where does the enzyme part actually come in, right? If what we're doing is taking ODEs and generating new ODEs to solve, right? Why does enzyme show up in there? Well, it turns out that in the second step here, right? In the second step, when you're solving that ODE that goes in reverse, that reverse solve ends up having this vector Jacobian product. And how do you do this vector Jacobian product? Well, there's many ways to choose how to do that. You can do, calculate the Jacobian with forward mode differentiation or numerical differentiation, transpose it, multiply, right? All the different ways that you can think of for calculating that. But of course, one of the best ways to do that is reverse mode automatic differentiation, right? Reverse mode automatic differentiation is a primitive that allows for calculating DFDU lambda times lambda, or DFDU transpose times lambda without having to ever calculate DFDU, right? And so what we can do then, this is actually where if you go back to this now, if you look at it, you'll see that we have this mutating code for this ODEF, right? And then what we say in here is auto-JACVec equals enzyme VJP. So what we're doing is we're saying, hey, when you're running the second part of the step, when you hit that point where you need to calculate the DFDU lambda, use enzyme right there, because that's the thing that supports mutation and does this fast. So we develop and we solve the ODE forwards, and the ODE that we're solving in reverse, we've embedded enzyme inside of there, and so suddenly the mutation and everything works out. And I think that some people, you might have thought that they were using zygote because all you did was zygote here, but aha, we've actually been using enzyme behind the scenes for like 4 years to be able to fix this problem, because a lot of codes are written with this mutation, right? We had a paper pretty far back that basically showed that enzyme is really the way to do this, because it gets you really high performance for if you use this as the way to calculate the vector Jacobian products in this context, right? Now, the whole point here, though, is that there's many different ways to do this adjoint method, right? So when I say the adjoint method, there are actually many different ways to be able to do each of the steps involved in this process. And they have very different scaling, and they have very different trade-offs in terms of robustness and memory usage. So, for example, for this one step right here, there's a question of, okay, when I say DFDU lambda, well, the U is a thing that you get from the forward solve. How do I remember what U is as I'm going in reverse? Well, there's 3 ways to do that. You can either be solving U prime equals minus F in reverse simultaneously, so you remember U. Mathematically, that's perfectly fine. You can store an entire dense output so you can interpolate it when you need to, or you can do some checkpointing thing, right, which is details. But the key point here, though, that we're able to show is that, hey, this is actually something that you have to think a lot about, because it turns out the first method, which is a method I'll go into a bit more detail, is actually numerically unstable. The second one uses more memory. The third one uses more compute. And so there's a trade-off in the different ways that you can do this calculation. And again, they're all embedding enzyme within there, but the way that you were actually telling, at what points you're going to tell enzyme to do differentiation of what, within this backwards ODE solve actually has a lot that matters on top of it, right? And to kind of highlight this point a little bit, I want to kind of go into, again, a lot of what we do with a lot of what goes on with the machine learning space kind of talks about different issues from what we do in a lot of the engineering space. So, for example, I want to kind of highlight that, there's this adjoint method which was brought forward at NeurIPS in 2018 for differentiating ODEs with respect to, parameters. It basically said a way to be able to differentiate U prime equals F is to solve this ODE going forwards and then solve this augmented ODE going in reverse. It is one way of choosing how to do all three of these steps, where you're doing the reverse solve by embedding a reversed version U prime equals minus F into step 2, and doing the integral of the third solve at the same time, right? So you can think about it as it's putting 3 steps together, and that's why it ends up with a 3-part ODE, which makes it so that way it's actually the most memory efficient method. And so you might go, oh, this is a great way of doing that. But it turns out that you can find equations for which it is unconditionally unstable. So for all delta t's, it will give you an infinite gradient. If you haven't seen the advection problem before, that's a very nice counterexample here. If you discretize the PDE for the advection equation, you have to choose what you're going to do. Your delta x, you're either going to use the forward value or the backwards value. This is upwinding versus downwinding, right? The analytical solution to this problem is a wave moving in one direction. So it should be very clear that if your analytical solution is just this value moving to the right, if you're only using the value to the right instead of the left inside of your ODE solver, there's no way you could ever get the solution, right? So there's a von Neumann analysis way of being able to calculate that, but at a high level, right? And so the key, though, is that if you are running this derivative going forwards and then you differentiate this process, right, you're actually reversing the direction of the wave, and so you actually have to reverse the ODE that you've chosen. And so if you ever try to do this reversing process that is described by this one way of calculating the adjoint, you will either have an unconditional instability going forwards, or you have unconditional instability in your adjoint expression. So either way, one of those will give you an infinite gradient and non-convergence, right? And so it turns out that when we talk about differentiating ODEs, we want to really use a AD in a very specific spot. We want to be able to tell the AD, do something right here, but we want to have a lot more control over the whole solution process, because naively using the AD is something that will not necessarily be stable, right? Now you might ask the question, well, why don't you just differentiate the solver? Great that you asked, because that also has just as many issues, right? And so I love this example, because I think a lot of people, like to say that automatic differentiation is floating point accurate or within machine epsilon, even though it's absolutely not true, and there's so many counterexamples against that, right? So here's a 2 ODE linear system, and when you differentiate it with the Julia solvers, you get these values, 11, 13 to 0.73. You can actually show that that's correct because you can analytically write down the solution and its gradient, right? Now, I'll tell you right now, when we do the derivative, if you're actually to check, if you calculate the derivative, we use different time stepping than when we do it in the normal solve, right? So we're actually correcting that derivative process there. So let's actually check with the JAX code, right? So the JAX code, you can implement the same example problem here. It's kind of, more steps to implement, whatever, but okay, let's differentiate that code, right? Well, the first thing that you could do is you can say choose the backsolve adjoint, which again, you don't necessarily want to do because that's the numerically unstable one. So the docs tell you don't use the adjoint method, right? Differentiate the solver. So remember here that the derivative is 11,013, right? And now we differentiate the solver, and it gives you 3,755, and you change the tolerances around, and actually that derivative is not changing at all. It turns out that on this problem, the differentiation of the ODE solver itself is actually completely separated from the tolerance of the solver, and it is a non-convergent algorithm on this problem, right? You can send the tolerance to 0, and you'll still get exactly the same derivative. And there's a very clear reason why. I could show you on the whiteboard if we have enough time. You can actually. So basically, the key idea is even if you're doing automatic differentiation to a solver, what the derivative process is doing is it's a discretization of an ODE solver itself. So you have to ask the question, is that solver that I've automatically generated, code gen, that solver that I created, is it numerically stable? And for even linear ODEs, you can find cases where the answer is no, that is not a stable solver, so therefore it's a non-convergent algorithm, right? And so, what we do in the Julia libraries then is we really focus on this numerical stability and convergence for these, ill-conditioned, difficult cases, because just applying automatic differentiation to a code doesn't, it will give you a solver, but that solver is not necessarily numerically stable. And this is a great example where you can show, not only can I give you a case where it has 60% error, I could actually, for any percentage error that you want, I could give you an ODE such that the JAX direct differentiation is going to give you that percentage error. Again, there's nothing wrong with JAX. It is implemented correctly. There are no errors there. It's just you can analytically show that automatic differentiation of solvers does not give you necessarily a convergent algorithm, and so you can construct counterexamples to arbitrary amounts of accuracy loss, right? There are other cases of this as well. For example, if you're trying to do the derivative of a chaotic system, right? Take the derivative of the Lorentz equation. So it turns out that when you solve a chaotic system, you cannot even guarantee that you have the forward solution correct, right? And when you solve forwards, you're getting what's known as a shadow trajectory. So there's an epsilon perturbation to your initial condition, and you get to see that solution, but you don't get to see the original solution. And so the idea that even for forward mode automatic differentiation, right? You're pushing along a derivative as you go along the trajectory, but when you're working on chaotic systems, your trajectory is not even right. So how is your derivative going to be right? It turns out that there's another way to understand some issues here as well, right? In that, so the Lyapunov exponent is the exponential rate at which your tangent space is diverging. And so if you have a positive Lyapunov exponent, well, what is the tangent space in terms of your derivative computation? Well, the tangent space is exactly the dual space in which automatic differentiation is doing its calculations. And so if you do automatic differentiation to a solver on a chaotic system, you will notice that your derivatives go to 0 exponentially fast, and that exponential rate is the Lyapunov coefficient, right? And so what we've done within our libraries is we say, oh, you actually have to do a bunch of corrections here. The process ends up being you solve over short time spans with a whole cloud of solutions. You let them diverge. You do a QR factorization to basically renormalize your gradient. And so you get a gradient with respect to the average of all possible solutions in some ergodic sense, right? But the point here is that, to be able to do automatic differentiation correctly, you want to have tools like Enzyme that can give you forward mode and reverse mode automatic differentiation, and you want to use that as a tool within the adjoints that you're generating, right? So, again, we are generating ODEs in order to calculate this derivative, right? So, we are doing the analytical adjoint method, but as you do the analytical adjoint method, for the ODEs that you're generating, you have to figure out, I'm going to put automatic differentiation in there too. So when I put automatic differentiation in there, what am I going to use, right? And so what we end up doing then is we have this whole set of numerically stable solvers with numerically stable ways of generating derivative processes, and we use the automatic differentiation in 2 different ways. One, to be able to tell the system, take this high-level code and generate this high-level code for the derivative, but then within the high-level code of the derivative, we embed the reverse mode automatic differentiation of Enzyme to be able to handle the mutation and all of that. And so it's a bit more complex than just differentiate the solver. But again, you can find a lot of counterexamples to where differentiating the solver is non-convergent. And so what we've been doing is developing a whole ecosystem where all of the different ways that you can write down these mathematical problems, be it a nonlinear solve, linear solve, ODE, and all these, we've been making it so that way the core numerics of the Julia language all support this automatic differentiation in a way that actually you can ensure that your methods are robust and convergent, especially in the context of ill conditioning, right? And so, I want to kind of go into this one bit on linear solve. So linearsolve.jl is a unified interface for linear solvers. If you give it a linear operator, A, and you just call solve, it will choose an algorithm. And the algorithm that it chooses is rather complex. It's dependent on what CPU you have. It's dependent on whether, if it's sparse, it's percentage of sparsity. I would love to go into details. That's a different talk, though, right? But but so here is a way of representing, let's solve a linear system, right? And so on this level of the mathematics, we can actually differentiate the solving of a linear system. You can change it to any other method, and then we can say, well, let's just use enzyme on this level, right? But the key here, I don't want to invalidate other talks, but like the key here is that you don't need to define differentiation on, say, Krylov.jl, because Krylov.jl is just one linear solver of the whole set of all different solvers that you can do, and this is now putting it at the mathematical level, so that way it's solver independent, right? And so any of the methods that you can slap into linear solve all get this process applied to it. And you can do this then, also for nonlinear solvers. So we recently just had this paper come out, actually just came out this morning, on nonlinear solve, which is about doing Newton's methods, right? And Newton's methods are for solving f of x equals 0, find x, right? And we talked all about how, there's different, okay, we use automatic differentiation within the Jacobians for how we do the Newton method, but we also support differentiating the Newton method itself and its solution. And now, you might expect for the backpropagation of this thing to maybe be expensive, but it turns out that if you think about it a little bit, the Newton's method gives you the same solution regardless of your initial condition to a certain extent, yada yada. But that should mean that that the derivative is actually, the derivative is not sensitive to what initial condition you're putting in, right? Another way of stating that is the derivative is actually only a function of the final point. And so this is what people kind of know as implicit differentiation. And so instead of telling the user, like, oh, use implicit differentiation.jl or some extra piece, we're able to say, this is a rule that is applied to this level of the mathematical problem. And so at this point right here, we need to do a reverse mode, but we do a reverse mode inside of this equation. So we'll start by solving the nonlinear system forwards, and then in reverse, we will build a linear system solve where we embed inside of there the reverse mode of enzyme. And so you can see the same kind of principle from the ODE case as well. So here you see that the person gives us a nonlinear system described by a mutating function of the input, f of u equals 0, find u. And if you just say, forward diff.gradient and zygote.gradient, it just works, even though, again, zygote doesn't support mutation. What it's actually doing here is to be able to do the vector Jacobian products of the adjoint, it will just use enzyme as needed for the mutation aspects and for optimizing the vector Jacobian products of that backward solve. And so, this is something that, it's both a pro and a con, because some people say this is quite complicated, but complicated usage of using multiple ADs together, more speed, more power, I'm all for it, right? So, but the key here is that, all these kinds of things where, you say, implicit differentiation gives you more performance, and enzyme has these benefits, whereas automatic differentiation libraries for machine learning, they can have these other benefits. What we end up doing is within this ecosystem, we have set it up so that way it will default to a combination that is efficient, but you can also then use keyword arguments to take control of this and be able to change it at will. And we do this across a whole bunch of different solvers, and so there's differentiation everywhere. This is what we do with the SciML organization, but the key here is that we don't just rely on differentiating the solvers directly, because differentiation of solvers is not necessarily numerically stable. And so a lot of the work if you go into a lot of the work that we do, a lot of it is all on the numerical analysis details about how do we stabilize this process in the context of many of these cases. And then finally, what we end up getting here is, as being just a standard part of the Julia ecosystem, right? Being just a standard part of the Julia ecosystem and everything else using the same automatic differentiation libraries, this means that we have some nice ecosystem integration. And so when people say, oh, we want to do probabilistic programming, there's no special ODE solver that's used with the probabilistic programming libraries or machine learning library, any of that. If someone wants to use an ODE solver within, say, Turing.jl context, well, Turing.jl is also using zygote or enzyme or these same pieces, and so you just slap the ODE solver in there, and it will do this process, right? It'll do this process of, when you're doing Hamiltonian Monte Carlo, it will take control of the ODE solve, it will take control of the derivative, and it'll do this special derivative process for you. It will still use an AD in there, but it won't be doing the thing that you would expect it to be doing. And so, so that's what we do with SciML, and that's why we use enzyme so heavily, and we bug Billy all the time for really random issues because we find a lot of weird edge cases as part of what we do. So thank you very much.
Thank you, Chris. Any questions?
So you showed like 3 steps to solving the G. Like, can we go back to
Yeah.
slide? I'm just wondering what G is.
Oh yeah, so I mean, yeah, this one doesn't have the full the full context behind it. So G is like a loss function, right? So when you normally do the derivation of the adjoint method, you say I want to take the derivative of a loss function, and so this is directly the dGTP is the derivative of the loss function with respect to your parameters, right? Now, if you want to do this within an automatic differentiation context, then you probably have other codes before you actually hit your loss function, and so when you change this to an automatic differentiation context, you just say my loss function is the identity function of whatever you get from the ODE output, right? And so then if you describe it like that, then it turns out that what you put as your enzyme rule, what you put as your derivative rule is just do the differentiation where you have you're differentiating with respect to the loss function being the identity multiplied by whatever the pullback value is. So, but in general, you can actually, again, like there's so many optimizations you can do. If you actually are doing this where this is my ODE, this is exactly my ODE, and this is exactly my loss function, you can actually optimize this a lot more by doing a direct differentiation of that loss function as part of the adjoint method. But it is mathematically equivalent, to taking all of the chunks of the reverse mode that'll happen after the ODE solver and putting those all into one step, right? But yeah.
One other question, which is you're using zygote on the outside, enzyme on the inside. What is the reason for that? Is it that you want to do some differentiation at a high level and some differentiation at a low level, or?
I mean,
interchangeable?
Well, okay. So part of that is that I'm lazy and I haven't updated my slides. At this point, we can actually do enzyme on the outside. With the enzyme rules integration, Billy helped us with that. We do have enzyme integration, so you can do enzyme on the outside as well. That's been available for 2 to 3 months, and I've shown on the discourse that it solves some of the issues where someone wants to use like some mutation in their loss function, enzyme will handle that, and then it'll handle the ODE solve, and it'll do this internally, right? So you can do that, but I kind of I haven't updated all these slides, but also B, I think it kind of highlights the fact that we are doing something a bit more than just if I put enzyme here and I use mutation, you go, okay, enzyme supports mutation. But if I put zygote here and I put mutation and tell you that it works, then you have to, then it makes your brain have to tick a little bit more and say, okay, well, what the hell is actually going on in this computation?
Other questions? Comments? Everybody just wants lunch. Well.
Know if this is quite the case, right? Because there's just some temporal horizon beyond which they're unreliable. It's not that you found an incorrect solution.
Yeah. So let me make that let me state that in a more numerical analysis kind of way, right? So the numerical solution to an ODE that is chaotic will have O of 1 error beyond a few Lyapunov times, right? And so the exact forward trajectory that you're getting is effectively O of 1 error. There's no guarantees that it actually has any convergence for any of the ODE solvers, right? But what you can show is that for hyperbolic systems, you can show that the shadowing lemma happens, right? And the shadowing lemma is that there is, for an epsilon ball around your original initial condition, there is another initial condition within that ball where you've accidentally gotten the exact numerical solution to that other initial condition, right? And so this gives you it's a fairly odd property, right? So this is the shadowing lemma property. But what it basically tells you though is that after a given Lyapunov time, you don't really have a clear way of, you have effectively a probabilistic description of the system, and you get a trajectory that looks okay, but where you are on that trajectory is almost completely random, right? And so what you can do though is you can correct it for this and say, well, so this means that the derivative with trajectories of exact ODE trajectories are not necessarily well defined then, right? Saying that I have the trajectory of the Lorentz equation system is not necessarily a good statement. Instead, what you can say is I have a sample of a trajectory that is on the Lorentz attractor, right? And so then from that statement you can say, well, can I differentiate with respect to the process of sampling solutions from the Lorentz attractor, right? And so so this means that the pathwise derivative is not necessarily well defined after many Lyapunov times, but the derivative of ergodic properties. So you notice that I changed. It's not the derivative of z of the solution. It's the derivative of the average of z, right? Because all the different solutions, they end up on the same attractor, and this attractor will move as you change your parameters, right? And so you can start to ask the question of how does this attractor move as I change the parameters, which is a derivative of the averages of the solution with respect to full times. And that is a well-defined property. But automatic differentiation will not naively do that. Automatic differentiation will naively calculate the derivative with respect to trajectories, but you'll have exponential growth of your error along that trajectory, right? Because again, two nearby trajectories will diverge exponentially fast. So that's why this forward-bound derivative ends up going to infinity. But if you do some renormalization process, you can cause this you can allow it to diverge a little bit and then pull it back together, diverge, pull it back together, very similar to how you calculate the Lyapunov exponents, right? You can do this renormalization process on the derivative process, and you can show that it converges to the derivative of the average. And so, so it's a very interesting case of, where, properties of chaos come into play, and chaos and how it relates to automatic differentiation is really nice again, because remember, the Lyapunov exponent is the exponential rate of divergence of trajectories in the tangent space, and the calculations of your derivative are all occurring in that same tangent space. It's like the dual that you're actually using for dual numbers, that dual part there is truly a calculation of the Lyapunov exponent. So it's directly related. So it is a fun type of example to just kind of show that just differentiating with respect to solutions is not necessarily something you can always rely on.
Thank you, Chris. I think we